Okay, so this is the DHCP. Anybody know what DHCP stands for? DHCP stands for Dynamic Host Configuration Protocol. These are the guys that automatically assign what we call IP addresses. You know what an IP address is? You heard it before? What is an IP address? Well, actually, it's a network adapter address. So anything that needs to get onto an Ethernet network, well, I'm sorry, anything that needs to get on a network is what we call TCP, IP, transfer control, called Internet Protocol. It's a sign of logical address called an IP address. It's a 2-bit number, or it's a big number. Normally here on a network will use 32-bit number. They understand that people don't understand binary. So what they do is they split it up into what we call octets, which is four decimal numbers. You'll never see anything but 255 because that's the biggest number you can represent 4 bits. And that would allow us to enter them in 4 decimal numbers. So we'll say like 169.152. If you're going to communicate on that network, it uses what we call TCP/IP protocol. You've got to have a address called an IP address. We have 2 versions. We have IPv4 and we have IPv6. IPv6 we're not even going to talk about. IPv4 is the one you'll see because that's what you get, because technically you're always part of a private network. You don't ever connect directly to the internet. You connect to an internet service provider like Bright House or these other people. So they assign you a IPv4 address, which is 4 octets. If you are on the internet, then you would use an IPv6 address, and it's not finding, it's not working. So we might have to go down to the lab and watch this. It's not finding my PC, my PLC. So I'll try one more thing. See if so every device that's going to be hooked up to the to a TCP/IP protocol has what we call a MAC address. The MAC address is the physical address that's built into the device. This is not logical. You don't assign MAC addresses. MAC addresses are built into the card. It's a 48 number, which has 2 to the 48 combinations, and that's what we're looking for. We're looking for the MAC address to pop up. So undoubtedly this is not working. So I'll show you all this down there when we go down to the lab and let y'all. So what happens is right now my DHCP server is looking for any device. Or, I'm sorry, all the devices are looking for a DHCP server. Oh, I know what's going on. This is one of those dumb moments. It's many of them. So this is the Ethernet cable. It's what we call a crossover cable. But, I don't even have it hooked up, so no wonder my PLC is not. Okay, there I am. So this is the MAC address. It's 000F. That's the MAC address. That's what Rockwell's look. This MAC address, it's got this PLC got a LCD display on it, and you can go back and you can look at the MAC address. All your other PLCs, the MAC address is going to be written somewhere on the label inside the PLC. So find the PLC when it's asking for an IP address. You're looking for the physical address, which is the MAC address. So these I'd have to come up here and find my PLC. So these are the different devices that's looking for it, but that's it right there. And what it's asking me for is an IP address. It's showing me the MAC address, and I got to see where my subnet's at. So I'm using an application called ipconfig, which tells me the IP address of my computer. So I signed in an IP address that made it compatible with my computer, and it should pop up in a minute that it's got it. So it's got it. So now I got to go back to RSLink. Know a lot more than what we're going to teach here, and we'll do that in the second class if you take that one. Another big problem we have is people understanding these guys right here. So these symbols here, what did we learn them at in the symbol right here? This anybody? We did look at symbols in this class already, right? Y'all got to help me out. I'm doing motor controls too. In motor controls, we refer to this as a normally open, and we refer to this as a normally closed. In PLCs, these are called examine if open, examine if closed. So this right here means this is true if we'll call it push button. And this right here, this is true if the push button is closed. These only deal with inputs. These does not deal with the stimulated relay contacts, and this gets people so confused. They'll call it normally closed, and that's okay as long as you understand it's an examine if open and examine if closed. And we'll show some big problems this could actually cause if you don't understand that. Program contacts that are controlled by the rungs output are simply called normally open and normally closed contacts. The examine if open and examine if closed are rung contacts that are controlled by physical input devices such as switches, push buttons, and sensors. So anything that I connect to an input port, we're going to have to deal with these instructions. If it's a contact on relay, it don't make any difference. We can call it normally open and normally closed. You can call it open and normally closed, but you got to understand the difference. That could cause big problems, and I'll show you all that. You're not required to know this, and this is what I just got through, so we're going to deal with that. I'll show you all that all down there. This is important to know. So anytime you start a new program, I'm not going to be able to download this to the PLC because I can't communicate with it. It won't do my IP addresses correctly. But well, anytime you start a new program, after you establish communication with it, the first thing you're going to have to do, this application controls can be used to program a lot of Allen-Bradley PLCs. Their RS Logic 500 series and their whole MicroLogic series. And each one of them has different CPUs. So what that means is that when we compile this over, we have to make sure we have the right compiler installed, right? Does that make sense? So the first thing you're going to have to do, anytime I come up here and I create a new program, once you've got communication, so I'm going to come up here, I'm going to, wrong. This is 5,000, guys. I'll show you all that too. So I'll come up here, I'm going to say I want to do a new program. So I'm going to do a new program. I'm not going to save this one. By the way, another thing that I don't like about this is RS Logic 500 is you don't give it a name until you download it or you save it. Most of your new applications, as soon as you create a new project or a new program, you get the name first. So right now, if I wanted to save this, this is when it's going to ask me for a name. So if I wanted to save this, I just hit save, and then it's going to ask me for what? Where I want to put it at, or a file name. Okay. If I want to create a new one, then up here, see the little arrow, the little blank sheet right here? Everybody, I click on that. And then the first thing it's going to ask me for, it's going to say, do you want to save this? I'm going to say no. It's going to ask me, what CPU are we programming? So what CPU are we programming? Because this way it's going to load the right compiler in, so it'll compile the instruction over for the processor. We'll be using two down there. We're going to be using a MicroLogic 1000. And the MicroLogic 1000 would be this guy right here. This right here is a MicroLogic 1100, and it's 1100B. So either one of these you'll be on. This class, it doesn't make any difference. So there's the Series B, and you'll see where I'm at. MicroLogic 1100 Series B. This is this PLC right here. Okay. Then ask me for a file name, and then what do I need to do now? The next thing we would need to do is configure the I/O. So I'd come over and click on this, and this would show me all the I/O devices that I can buy and strap onto the side of these things. And this guy allows me to put 4 devices out there. And once I've done that, then the next thing I'm going to do is what? Insert a rung, right? So here's our palette of instructions right here. The only ones we're going to start off with and using is this guy right here, which is inserting another rung. So I'm going to drag. Y'all know how to drag. Everybody know how to drag? How do you drag? Click the left mouse button and hold it, right? And drag it. Drag it down. See the green X come. Okay, that means that's where I can insert it at. It automatically moved the end instruction. So the end instruction is there automatically. You cannot put any device in the end room. This is automatically into the program. Most of your new ones don't show that, but that's the actual instruction that causes the program to actually loop and go back up to the first room. I'm stuck on this row. Next thing I'm going to do is we'll come in, put this. I'm going to come in here. This is a down drop. This is the way we put parallel circuits right here. So we call that a down drop. Everybody okay? You'll see where I picked that up? Now I want this to be inside that. We got 2 options. I can drag that in, or I can grab this red line and move it over. And then you'll see that. Everybody okay? Then I'm going to come down here. I'm going to pull another contact here. Then I'm going to come over here and pull an output. So you can do the whole rung without assigning addresses. Then what you got to do is you got to know the PLC. This PLC So the RS Logic 500 series, this is a rack-mounted PLC. It's a modular PLC. The first module is, I think we brought you up here. The first thing in the rack is the power supply. The power supply has no addresses. Then in what we call slot 0, one thing you got to learn in computers, everything starts with 0. Okay. So slot 0 is dedicated to the CPU. Slot 1 is dedicated to whatever you want to put in there. Now what we have on our PLC is we have a 16-bit, 16-port, 24-volt DC syncing input module. And then slot 2, we've got a 16-port, 24-volt DC sourcing output module, which we need to learn what this means. So if I come up here and look at these modules, when you get a chance, you'll see it says syncing and sourcing on there. So we need to understand that in a minute. Okay. So 16 bits. So what we would do if I wanted to address those is we start off with and that's what this is right here. So you'll find this handout right here. So this is addressing. This is the handout everybody should got. Y'all got that? We start off with what we call file type. What type of instruction is it? Well, right now we're dealing with input instructions and output instructions. So right now we would start off with an I. If I wanted to do an address and input, I'd start off with an O if I wanted to address an output. Then we put a file number. The file numbers for inputs and outputs are understand, so we don't need anything there. So y'all see that. And we'll put a what? A colon. Then after that, what do we put? The slot number. So right now, if I wanted to address this port right here, this is in slot 1, and I would start off with I:1. If I wanted to address this slot here, I would start off with I:2. And that addresses that slot, right? You understand that? Everybody okay? Then we follow up. Then the next thing would be a word number. So right now, these guys have only got one word on them, so we don't have to put it. Keeping these spots up to 2 words, so that would be 32 bits. So if I wanted to address the second 32 bits, then I would use a. So if I had 32-bit input modules, I would say input. This is not required for input modules because they can't move around. Then I'd put what? 1, and then I would put word 0. That would be the first 32 bits, or I'd put a 1 there indicating I'm looking at the second 16 bits. I'm sorry I said it wrong. That makes sense? We okay so far? Okay. So we can buy these modules even on this one. If I was looking at this one, I can buy a 32-bit module. Okay. So what we do is if it's only got one, then the word is, if it's only got if it's only got 16 bits or one word, then it's 0 and it's understood. If it's got 2 words, then I could say, okay, then I got 2 options. I could say input. Inputs don't need a data file number. Then I would put slot 1. Right, you understand that. Then I would put a what? If I come over here and do this, 1/3. When? So if it's only got one word, we don't have to specify a word number. So that's only. That's what we have. That's that dot right there. Yeah, because it don't have multiple words. So I've got a slot. It's 16. I got an input port. It's 16 bits. It don't have 2 words. So if I don't put a word, it's understood to be what? 0. If I've got 2 words, then I would address one of them like this, .0 slash some bit, or if it, then the other one I would say slot 1 and then I would say word 1 slash some bit. That makes sense now? So we're only required to put a word number if we're going to deal with a word, or if we're dealing with an input or output module that's got more than 16 bits. That makes sense now? Then this would be a bit number. So what we got is we got 16 bits, and we're using digital inputs. Okay, so this would be my input port. This bit right here would be addresses. What would this address of this bit be? Anybody know? 0. So it's just like the powers of 2s. Yeah, this would be what? 1. This would be 2. 2. It's not powers of 2s. It's number. It's an address. It's not a weight. It's not this 1, 2, 4, 8. That's if I wanted to convert this over. This is a bit number, right? Does that make sense? So it follows the 2 to the 0, the 2 to the first, the 2 to the second. This would be what? 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Y'all follow this? Yes? Okay. So what I would do if I look at the input module, we got all these screws on here. And we got 16 of them. And then one of them is going to line up to bit 10. So I'm going to come over here and I'm going to connect a push button up to this. And right now we'll hook it up to plus DC. Okay, and this is a screw. So if I wanted to see if this push button was closed, then the address, and it's in slot 1, then I would say input colon slot 1. We only got 16, so we don't have to specify a word number, and I'd put slash, and then I would put 10. So what I've done is I've addressed input 10 on the input module. So every one of these inputs have a bit address. It go to, if you wouldn't put multiple things on to, well, if you put multiple inputs into the same input, it would still be the same address. But if you're using different devices, right, understand what I'm saying? So we could technically come over here and do this. I mean, I could put 2 push buttons over here, and now we're setting up what we call a logic AND, but it still would be one address, right? You understand? So everything you hook up, you can hook up push buttons in series. You can hook up parallel. Usually we don't do it that way because I might want to use this push button later by itself. So normally every input device we give it its own input port. And so one thing you got to remember is that when you buy the PLC, you got to buy enough inputs to manage your system, right? You understand? And this is what's nice about a modular PLC is you can do what? Add more modules. A fixed PLC, you get what you buy. You get exactly what you buy. So if that PLC's got 10 inputs, that's all you got is 10. And if you need 11, then you messed up, right? Okay. So that's one thing. How many outputs do you need to run your system? We're on this one, I think we got 6, which is plenty for our labs. We got 10 inputs and we got 6 outputs on this. But every one of them is assigned a bit address, right? You understand? Well, it's exactly, it is a memory bit. It is a memory bit. So what happens is when the PLC reads the inputs, it puts them into a memory file. It's an to a bit in the PLC's memory. So the program does not read the inputs directly. It reads the input files. And then what happens, and we store the zeros into an output file. And then when the PLC scans the things, it just copies those into the actual true output. So a 1 would probably turn an output on, and a 0 would probably turn an output off. Of course, it depends on how you wire it. So that makes sense. So every terminal is assigned a bit address. So when I come over here and look at the actual PLC itself, right here, this is inputs. This is the input data file right here. And so this would be input 0, word 0. See the dot right there? There's 16 bits. 1, 2, 3. This would be input 0, word 1, input 0, word 3, input slot 0. Wait a minute. I thought the CPU was in slot 0. I didn't 6 fields. I mean, I didn't have 6 PLCs because it has no slot. So this guy's got integrated. This guy's got integrated input outputs on. So if it's integrated inside the CPU, the CPU does not occupy a slot number. So the CPU does not have a slot number. So your integrated ports that are built into the PLC itself will be in slot 0. This guy, though, first I/O port is going to be in slot 1 because in the rack PLC, the CPU has to occupy a slot, right? I understand. In a fixed PLC or a hybrid PLC, the CPU is not in a slot, but we've got to address the integrated I/O, right? That makes sense. So the guys that are going to be the integrated ports are going to be at slot 0. Are we okay? So not all ours, we're down there. They'll do that. And here's the output. Here's the output status. So we can fake it off, but so I still got an error. My error don't clear. Why won't my error clear? Because it says I don't have an operand entered or I don't have an address entered. So this right here, I have to assign it an address. So I'm going to assign it to an input, colon, right? These are internal ports, so they're going to be at slot 0. And then I have to select a bit. Everybody okay? Makes sense. Then I hit enter. Now what it's asking me for is asking me for a comment. And that's what it defaults to. Here's where you enter the symbol. Everybody okay? This makes sense? Okay. Now this has to be assigned. I'm going to assign this a different address. I'm going to say input slot 0. It don't have multiple words. No, I'm going to use 1 because I could have used 2. No, I just use 0. Now notice we enter them at the top, but as soon as we enter them, the bit address moves down at the bottom. So this is bit what? Can you see this, Kevin? 0. So this is what? Bit 1. Now this is a contact, but I'm going to assign it to this simulated coil down here. So I'm going to say output colon 0/0 because those are outputs. So the outputs are also at slot 0. And then I'm going to give this the name run. Did I say run? What did it do? I want to call this start. I can't do it now. Then I'm going to call this guy down here run. I'm going to delete this. By the way, to delete it, all you have to do, if you want to delete instruction, all you have to do is just highlight it and then hit the delete key on your keyboard, and then it's gone. Okay. I'm going to assign this to an output port because this is going to be controlled by that. And then I'm going to call this run. And then now all I have to do over here is call this what? Run. And it automatically assigns the address. Yeah, so this contact is being controlled by this coil right here. So when this guy here is energized, this contact right here will close. Now this is an examine if closed. We'll show y'all how you can edit that too, and show you how you can edit instructions. It's really cool. This is an examine if closed. This is an examine if open. This is a normally open contact controlled by this coil right here. Everybody understand that? I'm going to check the syntax. Says everything's okay. By the way, this is the model number of the PLC. So if you look at when I selected that PLC, if you looked at it on the left-hand side, it says it's a 1761. That's their model for this. So that really don't mean anything. Why they put it down there, I don't know. Now, if I could connect to the PLC, I would download to it. We'll go down and let y'all look at the lab and actually step y'all through this program right here. Okay? Now, why did I use, and this is where people get confused right here. Now, if I was connected, what I could do now is I would come over here. So right now we write our programs, the application, to write a program, the application has to be in the offline mode, right? And it'll automatically be in that mode when you create a new program. To download it, we would come up here and click this, and then I got two options. I can do what? I can go online. Now, if you go online right now, what's it going to do? It's going to automatically download whatever program's in memory of the PLC. I'm sorry, it's going to upload whatever program you have with the PLC, and this guy right here is gone. So be real careful there. So online is what we're going to do to look and see what's going on with the PLC. Then I've got download. Download means I'm going to take the program that's in my computer and I'm going to download it into the PLC. Which gets people confused because on the internet, when you want to bring stuff to you, you do what? Download. It's just opposite here. Download is sending it to the PLC. If I hit upload, then whatever's in the PLC will be uploaded into my application. Unfortunately, on RSLogic 500, when they compile it over, they do not store symbols and they do not store comments. So if you upload a program from the PLC, all your symbols and everything gone. The program is still okay. All your addresses are still okay, but you don't get all this other neat stuff that you get. So this is our first program, guys. Very simple. It's just a start-stop station, and we'll talk about why I'm using an examine if closed. A stop button has to be a normally closed push button. Anybody know why? Yeah, but why? Why does it have to be normally open? Why could it, normally closed? Why can't it be normally open? A stop button. Just a stop. E-stop would be the same way. E-stop's got to be normally closed, and a stop button. Normally on motor controls, an e-stop is drastic, right? You understand? But most motors, if we start them, we're going to stop them without an e-stop button. So we got a stop button. A stop button has to be normally closed. Anybody know why? Well, PLCs, the way PLCs look at it, and we can look this up, if I use a normally open push button, what happens if the wire what happens if the wire opens? It's going to be normally open, and we couldn't stop the circuit, right? You understand? So what we're doing is we're saying this is an examine if closed. So it means this contact is true if it's closed, and we'll have to go down there and show it to you because, like I said, I can't connect to my PLC. So let's see. Comms. Who's active? One, or we can save it right here. Everybody okay? We used to call it the 10-rung rule. So save every 10 rungs because these things are applications, they're computers, and they lock up every once in a while, right? And you've done 50 rungs, and your computer locks up on you, and you do what? Lose everything, yeah, get upset. So we do some that's over 10 rungs in this class, I think, when we get into timers and counters. Right here, the little down arrow, I'm going to come over and hit download. Now, this is where it's going to ask for a name. If you save it, it's going to ask for your name, but if you don't save it, it don't ask you for a name until you download it, which most of your new applications, you have to give the project a name as soon as you create a new project. So the way the S7 works is you give the project a name, and then you establish the communication. So we'll call this play. And we'll save it. Now what we're doing is we have the PLC in what we call remote mode. Remote mode means you can switch the PLC between the 3 modes with your application. If we looked at if we had a compact logic, it's got a switch on the front of it that says program remote offline. I'd have to look at it. If you put it on program, then it's going to run the program, or you have to put it offline to upload it, right? If you put it on remote, then you can control it from your computer. What's nice about the key is that you can put it in program and you can take the key out, and then nobody can do what? Can upload what we're doing now. Download the program. Right now, the PLC, if we looked at the processor, it has no name. I'll show you how you can give the processor a name. Then it's going to automatically switch it into the run mode. And then it asks me, do I change back to the run mode? Yep. Do I want to go online? Now, when we go online, so the PLC is running the program right now. Online means your computer is hooked up to it, and you want to see how the program runs. So I'm going to go yes. Now notice automatically your 2 rungs turn what? Green, indicating this guy's up and running. So what I'm going to do is I'm going to close switch 0, which is supposed to be a normally closed switch anyway, and notice it showed it what? Yeah, it showed it green, which means my signal has made it through that device. And then what's it waiting on? It's waiting on my start button, right? Everybody see this? Well, the run is a contact controlled by a relay. It is not an input. So notice this guy starts with what? I. This card starts with O. So this is a contact that's being controlled by this simulated coil. This is not a real coil, it's simulated. But what we're going to do, it's going to control an output. You understand? Are we okay so far? Yeah, when this guy goes true, or when the run goes true, then this guy, we say it's energized, even though technically it's not. It's energized, which should do what? Close this contact. So that right there is I'm simulating a normally closed push button. So it's true to start off with, right? You understand? Okay. So that's why I'm using an examine if closed instruction, because I'm using a normally closed push button. Now, why do we use normally closed? Is that if the wire opens, the circuit will de-energize. If I use an examine if open, if the circuit open, we wouldn't be able to do anything. We couldn't stop it, and I'll demonstrate that. So normally for a stop button, we use that right there. In motor controls, you'd go crazy because it looks like, because you want to see it as a normally closed contact, but that's not a normally closed. That's an examine if it's true if it's closed. So is a stop button normally closed? Yes. And we're using examine if closed or if true if it's closed instruction. This guy right here is a normally open push button, and it's what we call an examine if closed instruction. But I'm going to use a momentary contact, so I'm just going to come up and touch this thing, and it sealed itself in. Now, what we saw is what we can do is, if I can break up my camera, is the only thing I really don't like about the 1100, it is a nice PLC, is that it uses an LCD screen, but it's not backlit. So that means if you were in a dark place, you wouldn't be able to do what? See anything that's going on. Oops, I need to select the camera first. We'll see if there's a force that turns on. So what's nice about this, oops, got a problem, guys, because these are supposed to be connected too. So undoubtedly I got something that's came loose. Oh yeah. So what you can do right off the bat is, so a PLC will help you troubleshoot, because if I'm over there hitting the push button, then I should be seeing on my PLC showing that the push button's going through. So a lot of times we can check out the wiring of a circuit if we got broke wires or stuff without ever getting the meter out. And also it shows me that output 0 is true. So output 0 is turned on, which is what we were using for the program. Can y'all see that? This is this guy here's got, if I can zoom in on the outputs. So every loop is an output. So it's got 1, 2, 3, 4, 5, 6 outputs. My inputs, I don't know if I can show y'all that or not. They're up across the top. Just focus in. It's got 2 commons, and that's what happened. One of my commons came loose, which we're going to talk about in a second. So it's got it's got a built-in DC power supply. We call this an AC DC relay PLC. It's got its built-in power supply, so it hooks up directly to Alabama Power. Or here we got TVA, if I can get it to focus. No, can't. Let's see if we can get it in there. So they call it L1, L2, and then these are the commons here. We'll talk about how we wire this thing up. So the problem is one of my commons popped out. This is mounted on a, Pesto calls it EduTrainer. It's set up to handle 16 inputs and 16 outputs. So I've got these switches down here. This is where I'm simulating my inputs on. I can get it to focus. And this is where we could actually hook up true inputs right here. So we could actually hook up true push buttons, and that would wire it up to the PLC. This is output, so it's got LEDs down here that light up, but this is where I could actually hook up true output devices to this trainer. But this is not the trainer. This is the mount for the PLC. I'm sorry. So this PLC does not have 16 inputs, and it does not have 16 outputs. It's got how many inputs did I say? 10, and how many outputs? 6. Okay. So one of the labs you're going to do is when you get assigned to a station, is you're going to say how many inputs does your PLC have and how many outputs does your PLC have, and somebody's going to put 16, right? because they're not looking at the PLC, they're looking at the mount for the PLC. And you can buy more than these. So if I had 32, then I could buy another one of these panels and then have the cables to actually wire it up. So here's my stop button. So let's stop it. So what I can do is I can simulate a normally closed by just flipping the switch over to one side. But the output's not on. Then this simulate a momentary contact push button. I just push it and then release it, and you saw the output turn on. But we can also see it up here, right, on the PLC itself. Most of your PLCs have gone back to LEDs now to display if the inputs are true or the outputs are true. So. It's not going. Oops, sorry. There we go. So this is just a demonstration of a PLC that has 8 inputs and 8 outputs. Now, originally, when they came out with modular PLCs, I'm trying to find the one in your book where they show the output connections. This is the way most PLCs, or all PLCs that I've seen lately, that goes on. So what we do is we have the input device itself. So these are just simulating input devices, and these are loads that we have connected to the output. So what type of loads could that be? It could be lights. It could be another relay. It could be. What we find out real quick is that PLCs do not do away with relays. PLCs can only output. Rule of thumb is around 2 amps per output port, but that would be enough. It wouldn't be enough to run a motor, but it would be enough to bring in a relay that runs a motor, right? Does that make sense? So they haven't done away with that. Well, what we have is we have the power rail inside the PLC. So this is inside the PLC, and then we have the way that we connect input devices to the PLC. Now, if we have AC inputs, and if we have AC inputs, then we're not worried about anything. Then I would just put an AC voltage source like this, right? And that wouldn't be true. The inside of the PLC never runs off of AC. So this right here would actually be we have an internal battery in here, and then we would bring an AC voltage source in here, and then it's converted over. That makes sense. Okay. If I'm dealing with DC, then we've got 2 options. The inputs could be set up like this, where I come over here and I bring the negative in here, then I would put the positive over there. That makes sense? Yes or no? Okay. So current flow would be this direction. I could also, if I buy the right module, I could also, my PLC might be set up like this. Did I draw it the same way? Did I reverse it? Hopefully I reversed it. Yeah. So here, the actual inside the PLC, its port is using the minus, and then the inputs are using the plus. This is a common connection right here that goes down to all my input devices. This term has came from from digital, but this is the way it works in PLCs. If you use a plus over here on the input device, we call this sourcing. So sourcing in PLCs means we're using a plus as the common, right? Now common is just a common connection spot. This is not ground. Then if it uses a negative as the common, this is referred to as syncing. So if I'm using sourcing input devices, then the PLC inputs have to be syncing, right? Does that make sense? Yes or no? Yes or no? This is very important, guys. The book does a very poor job of this. If you don't understand this, you're not going to be able to wire PLCs. So over here, when I look at this input device right here, it says it's a syncing input. So it means though all those inputs are connected to minus. So that means on all my push buttons, I better connect to what? I better connect to plus. So if your input port is syncing, then your input devices have to be what? Sourcing. Or vice versa. To get the current flow, right? So if I came over here and I bought a sourcing input port, so that means sourcing means the plus points this way. So my input port is what? Sourcing. So my input devices have to be wired to do what? You know, syncing or wired to sync. And this came from digital. When you take digital, this will make sense, but this came up from that. So if my devices use a negative common, that's going to be what? Syncing. If it uses a positive device, it's going to be sourcing. The port has got to be opposite so we can have current flow through the port. So standard way over here, standard the way we do over here in the good old USA is normally we have a syncing input. So that means the negative points this way, right? And then that means when I connect up so you have to wire your inputs. So what that means, you have to take that positive output and you have to run these out to all these push buttons. So that's the push button right there. Then I have to run that wire out there. I have to do that. The negative is internal, but I have to run the sourcing for the push buttons. So our PLCs and every PLC that I've ever worked on over here uses sourcing inputs. So that means your PLC inputs ports themselves have to be wired. They're either pre-wired syncing or you wire them syncing. That makes sense. Over here, this is the way we do it over here. This only applies to DC because AC has no polarity. So over here, if we're going to use DC outputs, the outputs are sourcing. That means what do I have to do? I have to wire all the outputs to the negative. So I have to hook up my outputs what? Thinking. These are Alabama Micrologic PLCs. Y'all just have to come up here. So y'all come up here. The red line, we got a meter. This guy here, so this PLC, we say it's AC, so it powers up AC. It's got its own power supply, and then DC would define what we have on our inputs, and then this has relay outputs. Now the advantage of relay outputs is you can make them AC, you can make them DC, you can hook them up syncing or sourcing. So this is my power supply right here. This is the minus. Now what's unique about this, can y'all see this? Y'all need to look real close. Y'all looking? Yeah, but what we're doing is we're bringing this guy right here. Which is the minus. No, the black is just a wire that I had. Okay. So what we're doing is we're setting up the common for my inputs. And I'm running, this is the minus, and it's got two commons on it. Can y'all see this? Y'all going to have to get up and look. I know y'all can see it. So it's got this DC common right there and this DC common right there. Can y'all see it? So what this PLC is that we can set it up, the inputs up to either be, the input port to be up either syncing or sourcing. So, but they run in groups. So this is 1, 2, 3, 4. So this is 4 ports right here that we can set up either syncing or sourcing. And then we have 6 ports right here that we can set up as either syncing or sourcing. But I'm running the minus over there. So I'm setting up my input ports to be what? Syncing. So that means these guys right here have to be sourcing. So this is the minus right here. Now this one's easy to see. This wire's got a red stripe on it, so guess what that probably means? That's the plus. Now down here, since this is a relay output, we can, let's look at the commons on here. Y'all look real close. It should have AC/DC, 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 AC/DC. Y'all see that? Okay. So what that means is if I wanted to use these relays, if I wanted to output AC, then I could jump the L2 over, right? Understand? But what we have is we have the plus jumped over, and every one of the commons are jumped together. And so we're putting the plus up there, so these inputs are what? With the plus. So that means every device I hook up to this guy right here, I'm going to have to put the negative on the other side. So if my outputs are syncing, if my outputs are sourcing, then my input devices have to be wired to do what? Sync. Right? You understand that? If my output up here, we have these set up to sync, so all these switches down here have to be set up to source. Everybody understand that? So syncing and sourcing, and look at this guy over here. Look at the input modules. What does it say up there? What does it say? What are those? So those you have to buy, right? It says they're what? Should say syncing up there on the input module. DC sync, and then the output says what? DC source. So there you buy the modules depending on the way your company runs things. It all depends on the way your company runs things. Over here, we predominantly run syncing inputs and sourcing outputs. Okay. So who runs this wire right here? Yeah, you do. You have to run this wire to all your input devices. So the book doesn't do a good job of that. It throws that syncing sourcing out there, but it don't tell you that, and that's very, very important. So what if you got syncing inputs and you go out and buy a sensor that's a syncing sensor? So it ain't gonna work, right? You understand? Not gonna work. So when you buy sensors, usually, and that's something you need to look at when you buy these electronic sensors. You can buy the same sensor as either what? Syncing or sourcing. So you need to understand how your plant runs, right? How they run. Predominantly over here, and you can get a meter out. You can get a meter and measure this common going to your other devices from the other side. If it measures plus, that means the device is what? Sourcing, right? But that's very, very important. Does it apply to AC? No, AC has no polarity. If you got AC inputs and you got AC outputs, this means nothing because AC has no polarity, right? Usually we use L2 for the common, and then we use L1 to hook it out there. But more and more and more PLCs are going to pure DC. Because why? First of all, you've got a DC power supply anyway, right? So you already got it that. Plus, in 24 volts is the standard voltage now for the PLCs. 24 volts DC. But if you get into older situations, a lot of your control devices were AC devices. So that means odds are, if you get into older applications, then you're going to have AC inputs or AC outputs, right? Your applications, you'll probably have DC inputs, and the outputs depend. There's still a lot of DC stuff out there. So what's nice about this guy is you can set up every output bit is either DC. You can set it up syncing, or you can set it up AC. That's the advantage of relay outputs. The biggest problem we have with relay outputs is, number one, they're electromechanical devices, so they can fail things. And another thing is they're not fast. You can't switch them real fast. So relays are slow compared to solid state. So, are we okay? Syncing and sourcing. Y'all okay there? Okay. So we'll go back and we'll look at our PLCs. So this is basically the way it looks. So the inputs feed the CPU. These don't show them wired. By the way, when you draw your input connections, you have to use the symbols that's used by relay logic. So here I have a normally open push button, followed by a normally closed push button, followed by a what? Normally open pressure switch. I'm sorry, normally open float switch. Pressure switch is half, and then a normally closed limit switch. Over here we have a what? What's that a symbol for? This one right here. These are loads. Loads are not going to be diodes. That's the data of a solenoid. A solenoid. Can I show you a solenoid? Brought my little thing up here, put the nail in there, sucked it up in there. This is a symbol for a, probably a motor starter, yeah, or motor, yeah, a contactor. This is the symbol for a what? Right. This is a symbol for a That's a symbol for a horde. Or a speaker, usually. So on your lab book, it's set up for 120 volt AC. That's not what we have. We'll go down and look and see what we got. Ours use so on your diagrams on your lab, this is going to say 120 volts DC. Do we have that? No. So what you're going to do is you're going to mark that out and write what? Common. And then this is the way our PLCs are wired. So the input ports are wired to sync. So the input devices have got to be wired to do what? Source, yeah. So see the plus goes out there. Over here, I forgot what it says there, but this is the way we connect. We got two. The 1100, the MicroLogic 1100 uses sourcing outputs. So that means we're going to have to run this wire out here to do what? They're actually got a motor. Now the 1000s runs 120 volt AC outputs. So y'all got to be careful on that thing. So on the 1000, this would be the same, but on the 1100, then we'll put this symbol right here. And this is a symbol for what? That's a symbol for an AC voltage source. So this is not going to have polarity. So this is the way the 1100 is wired. Now on ours, we don't have this many inputs. We got how many inputs? 10 inputs right here. And then how many outputs? 6. Well, why did I start with 9, right? Stop with 9 when it's got 10. Yeah, it starts with 0, right? What time is it? 8:30. Okay. So we'll go down there and let y'all play with it. This is a typical scan. So first thing we do, number one, is we read inputs. We run the logic in the ladder, in the rung, and then it updates outputs. And then what does it do? Read inputs. And right here it's doing what? It's running the logic, running the program. And then it does what? Yeah, updates outputs. And then what does it do? Drops down to the next rung. What does it do? Read inputs, runs the program logic, updates outputs. And then it does this, all the rungs in the program. And then it finally does what? Hits the end. And when it hits the end instruction, what does it do? Yeah, it goes back to rung 0 again and runs it just constant. This is called a scan time. Most PLCs, I'll show you how you can measure those, where you can actually see the scan time, how long it takes to execute your program. And then we'll talk about some problems we might have. Let's go down and look at the lab.